So good day everyone. My name is Castro from DCPT 31 and today I'll be tackling to you some discussions on our final examination on microprocessor. So, to introduce to you our topics. As we all know, in today's digital world, computers and smartphones are everywhere, powering our daily lives. So at the core of these devices is the CPU, which is our first topic, or the central processing unit, which acts as the brain of the system. So it is responsible for executing tasks, processing information, and ensuring everything runs smoothly to truly understand how computers and smartphone works. So we need to explore how the CPU operates, how it has evolved over time, and how it interacts with other key components like the memory and GPUs, which we'll talk about later also, along with the overview of CPU and the evolution of it. Then lastly, we'll discuss the SAP1 operations and its programming. So, along this way, we'll also discuss some examples of each topics and some major takeaways. So first up, how CPU works. Now, as we all know, the CPU is at the heart of the computer. It handles all critical tasks required to run software and process data. So it operates in a cycle of fetching instructions, decoding them, and executing commands. This process is tightly synchronized with the help of a clock wire that turns on and off billion times per second. And the CPU communicates with the RAM or the random access memory, which temporarily stores data, retrieving instructions and information as needed. So for example, when you open a program, the CPU fetches the program's data from memory and processes it to display on your screen. Now inside the CPU, the arithmetic logic unit or the ALU is the one that performs all the mathematical and logical operations, while the control unit ensures all components work together seamlessly, and registers, which are small but extremely fast storage units within CPU. It temporarily holds data during processing, enabling quick access. Although modern CPUs are vastly more powerful and capable than earlier models, their basic function, moving and processing data efficiently, still remains the same. Now that we understand how CPUs works, let's examine the leading brands. So this is the most common in both computers and smartphones. So in desktop and laptop markets, the most famous ones are the Intel and AMD. So Intel's core processors such as i3, i5, i7, and i9 are widely recognized for their energy efficiency. They are ideal for gaming, video editing, and general productivity. And in contrast, AMD's Ryzen processors stands out for their affordability and multitasking power such as R3, R5, R7, and such. They offer more cores for handling multiple tasks simultaneously. And this makes AMD a popular choice for professionals working in fields like video rendering or 3D design. And the choice between Intel and AMD often depends on whether the priority is single core performance or handling numerous tasks at once. Now, in the smartphone world, Qualcomm, Apple, and MediaTek lead the market. Qualcomm Snapdragon processors power many Android smartphones, offering a balance of speed, efficiency, and gaming performance. Meanwhile, Apple's A-series chips, such as the A15 Bionic, are exclusively designed for iPhones and iPads, delivering unmatched performance and energy efficiency. Now, MediaTek, on the other hand, is known for producing cost-effective processors for mid-range and budget smartphones. These brands cater to different needs, from high-performance gaming and multitasking to energy-efficient daily usage. Now, by understanding how CPUs work and the differences between the major brands, we can now appreciate more the role of these processors in play in powering our devices that shape our digital lives. Whether it's a desktop computer, gaming laptop, or a smartphone, the CPU remains the driving force behind it all. Now, talking about the evolution of CPU. So in this evolution of CPU, we'll compress or we'll explore it in four parts. So for the first part, which is the evolution of CPU processing power. Part 1, the mechanics of CPU. So, the evolution of CPU showcases a transformative journey from the mid 20th century to today, starting with the introduction of Intel 4004 in 1971, a 4-bit processor with 2,300 transistors capable of 46,250 to 92,500 instructions per second. CPU have significantly progressed in both design and performance. This breakthrough, only consuming only 1 watt of power, revolutionized computing by offering compact, efficient processing compared to earlier behemoths like ENIAC, which weighed 27 tons and consumed 180 kilowatts over or daily. Over decades, advances in miniaturization, binary data representation, and processor architecture have paved the way for modern CPUs, like the Intel Core i9-7980XE, achieving over 80 billion instructions per second. So this leap reflects a 900,000 fold increase in processing power driven by innovations in transistor density, instruction sets, and the optimization of the fetch, decode, and execute cycle, all synchronized by increasingly sophisticated clock systems. Now, moving on to the part 2, which is the rise of x86. Now, as the 1970s unfolded, CPUs underwent a significant evolution, transitioning from basic designs to more sophisticated architectures. The progression was marked by Intel's 8008 in 1972, an 8-bit processor that introduced pivotal features like indirect addressing and interrupts, enabling advanced software techniques and multitasking. The 2008's innovation paved the way for the Intel 8080 in 1974, regarded as the first modern desktop CPU with enhanced speed and memory capacity. And by 1978, Intel's groundbreaking 8086 with its robust 16-bit architecture and segmented memory laid the foundation for the iconic x86 architecture. And these advancements cemented Intel's role in defining modern computer and set the stage for future innovations. Now, moving on to part 3, which is the origin of modern operating system or OS. Now, during the 1960s and 1970s, the concept of multitasking began to take shape in the world of mainframes, starting with multiprogramming, a technique where the system switches between programs during idle times, like waiting for hardware input. A technique where the system switches between programs during idle times, like waiting for hardware input, has evolved into time-sharing system, allowing multiple processes to run seemingly simultaneously. And by the late 1960s, true multitasking appeared with systems like DEC's, PDP-6, and IBM's OS-360 MFT, with Multics playing a pivotal role in shaping Unix. And the emergence of multitasking introduced challenges in CPU management, leading to the development of cooperative and preemptive multitasking. Preemptive multitasking, in particular, resolved stability issues by ensuring each process was given a fair time slice of CPU power. And with growing software complexity, the need for memory protection arose, and the Memory Management Unit, or the MMU, was introduced to safeguard processes from accessing each other's memory. This, along with the implementation of virtual memory, laid the foundation for modern operating systems, enabling them to efficiently manage resources and ensure security while fostering the growth of powerful multitasking systems like the Macintosh and IBM's PC-80. Now, moving on to the last part of our four-part series of the evolution of CPU, the 32-bit processor, pipelines, and cache. Now, by the mid-1980s, the demand for more powerful software, such as word processors, led to the rise of 32-bit processors. In 1984, Motorola released the 68020, a true 32-bit processor that became popular for desktop computers, offering 32-bit internal and external data buses as well as 32-bit address buses. Now, around the same time, Intel also introduced the 8386, a 32-bit processor with an emphasis on backward compatibility and advanced memory management, capable, capable of addressing up to 4.2 gigabytes of memory. The 8386 architecture also introduced instruction pipelining, a technique that broke down the instruction cycle into sequential stages, allowing the CPU to process multiple instructions simultaneously. And to further improve CPU efficiency, techniques like out of order executions and branch predictions were developed. Caching also became a critical component in memory management, storing frequently accessed data in high-speed memory to boost performance. Now, this advancement in CPU design, from pipelining to caching, marked a significant leap forward in processing power and efficiency during the 1980s. So now, the evolution of CPU processing power has been a journey of continuous innovation, beginning with early systems that focused on simple arithmetic and basic computing tasks. The 1950s and 1960s saw the development of early mainframes and the transition from vacuum tubes to transistors, which paved the way for more efficient processing. In the 1970s, microprocessors emerged, revolutionizing computing by integrating all CPU functions on a single chip, leading to the rise of personal computers. Meanwhile, the 1980s brought the introduction of 32-bit processors, with improvements like pipelining and memory management units, and caching, increasing processing power and enabling multitasking. Over time, innovations like caching, out-of-order execution, and advanced instruction sets further enhanced CPU performance, laying the groundwork for the more powerful processors we use today. Now, moving on to the overview of GPU, which is the Graphics Processing Unit. Now, a graphics processing unit, or a GPU, is a specialized hardware component designed to accelerate the rendering of images and videos, as well as perform high-speed calculations for graphics and data processing tasks. GPUs are particularly adept at handling complex parallel processing workloads, which make them ideal for applications such as video games, cryptocurrency mining, and AI computations. Unlike CPUs, which excel at sequential task executions, GPUs break down large tasks into smaller, simultaneous operations, utilizing thousands of cores to process massive amounts of data concurrently. This parallel processing ability is what gives GPUs a distinct advantage in areas where multiple calculations need to be performed at the same time, such as real-time graphics rendering or machine learning model training. GPUs are also designed with specialized cores that optimize performance for different computing needs. For example, CUDA cores or CUDA are used for general computations, while Tensor cores handles AI and deep learning tasks, and ray tracing cores are dedicated to simulating realistic lighting and shadows for high-quality graphics. These innovations make GPUs highly efficient for modern computing demands, especially as technology continues to evolve. The increased performance capabilities of GPUs have led to their integration into various industries beyond gaming, including scientific research, data analysis, and autonomous systems, where large-scale computation and processing are required. Now, for some examples of GPU. Some well-known examples of GPU include the NVIDIA GeForce RTX series, such as the 3080, 3090, and the 3090 Ti. But now, it can go up to even higher level like the 4090 and now the new release 5090, which are powered by the GA102 chip. These GPUs differ in the number of cores and memory capacity, providing varying levels of performance for different tasks. For, inta- for instance, the 3090 Ti is equipped with 10,752 CUDA cores, offers extreme computational power, and is ideal for demanding applications like 4K gaming, AI model training, and high-end simulations. The versatility of and power of these GPUs make them a go-to choice for professionals in fields like gaming, content creation, scientific research, where superior graphical performance and processing speed are crucial. Now, we'll talk about the last topics of our discussion, the SAP1 operations and programming, or the simple as possible one. So, the SAP1 or simple as possible one is a basic microprocessor that follows a very simplified architecture, allowing programmers and beginners, or rather beginning programmers, to understand fundamental concepts of computer architecture. It operates by executing instructions from memory. Using a fetch execute cycle, the SAP1 has several key operations, including fetching an instruction from memory, decoding the instruction to determine which operations to perform, and executing the operations. So, for example, during the fetch operations, the program counter or the PC holds the address of the instruction to be fetched from memory. This address is passed to the memory address register or the MAR, and the introduction or the instruction is loaded into the memory buffer register or the MBR. Once the instruction is fetched, it is passed to the instruction register or the IR, where it is decoded to execute the appropriate operation, such as adding or storing values in memory. Once the instruction is decoded, the SAP1 proceeds with the required actions, such as adding or storing data. For example, in the case of add instruction, if the instruction is add 5, the contents of memory location 5 are added to the accumulator, which holds intermediate data. The result is then stored back into the accumulator. Similarly, in a store operation, data from the accumulator is transferred to a specific memory location. The fetch execute cycle then repeats for the next instruction. Now, this systematic approach allows the SAP1 to carry out arithmetic and logical operations by performing simple fundamental tasks, making it an excellent tool for learning how processors function, or also how a mini computer functions. And the SAP1's simplicity also allows students to visualize, or the programmers to visualize, the flow of data through the microprocessor. As instructions are fetched, decoded, and executed, stu- the programmer can track how each component of the microprocessors works together to carry out operations. By following the basic steps of fetching, decoding, and executing instructions, users will be able to gain valuable insight into how complex microprocessors operate. This basic architecture is foundational for understanding more advanced processors, and the SAP1 serves as a stepping stone for grasping key computer architecture concepts, and also help beginners understand how computers work and how computers interact with memory input and output, and most importantly, it helps beginners to understand the most basic computer concept, since it is designed to help understand how computer works. Now, moving on to the programming part of the SAP1. Now, SAP1 programming involves writing machine level instructions in binary format that the SAP1 microprocessors can understand and execute. These instructions are stored in memory and executed one by one. Programming the SAP1 typically requires using a set of predefined opcodes that map to specific operations, such as loading data into registers, performing arithmetic operations, or storing results. The instructions are generally composed of an opcode and an operand. For, exam- for example, an instruction like LDA3 or load value will load the value at memory location 3 into the accumulator. Programming with SAP1 allows beginner to experiment with simple operations such as loading, adding, and storing data. For example, if you want to let's say, add two numbers, the programmer might write might write a sequence of instructions like LDA1 or load the value from memory locations 1 into the accumulator, followed by add 2, which then add the value from memory locations 2 to the accumulator, and finally STA3, which stores the result from the accumulator into memory location 3. These instructions illustrate how data flows through the SAP1 processor from memory to the accumulator, and how the result is stored back into the memory. Now, through SAP1, beginners or learners will be able to gain an understanding of how high-level programming tasks breaks down into simple machine-level operations. The sequence of steps in programming SAP1 mirrors the core function of processors and computers in general, teaching key concepts such as data manipulation, memory addressing, and execution flow. And as programmers become more familiar with the basic operations, they can explore more complex sequence and algorithms, deepening their understanding of how processors work. And this form of low-level programming also helps bridge the gap between high-level programming language and the hardware that execute those instructions. So, in this long discussion for the final examination of our microprocessor lecture, we explored many topics, such as the core concepts behind CPU and GPU architectures, the evolution of processors, and how microprocessors like the SAP1 operate and are programmed. We began with an introduction to how a CPU works, focusing on its role in executing instructions through a fetch decode execute cycle, enabling the computer to carry out tasks efficiently. The evolution of CPUs was also broken down into core parts, starting with the early days of basic processors, moving through the adoption of 32-bit processors and their corresponding features like instruction pipelining and memory management, and ending with an advanced technique such as out-of-order execution and cache coherence. These advancements were crucial in boosting the performance of CPUs, making them capable of handling more complex operations as software demands grew. We then shifted to the GPU, a specialized hardware designed to accelerate graphics rendering and perform parallel computation, particularly in gaming, cryptocurrency, mine, cryptocurrency mining, and AI. GPUs excel at managing large-scale data tasks simultaneously, making them different from CPUs, which are optimized for sequential processing. And we also discussed the examples of CPU, like for the desktop, we have the Intel, AMD, and for smartphones, we have Qualcomm, MediaTek, and A, Bionic, or for the Apple. And for the GPU, we have the NVIDIA, like those types. So, the rise of GPUs has brought about significant innovations, such as tensor cores for AI tasks and ray tracing for realistic graphics, allowing them to handle increasingly sophisticated computations. In contrast to CPUs, GPUs are built to manage tasks that require massive parallelism, showing how computing systems are evolving to tackle complex data-heavy problems. Now, my main key takeaway from these full topics, from our exploration of CPU and GPU architecture, the evolution of processors, and the basics of SAP1 operations and programming, is the importance of understanding how computing systems have developed to handle increasingly complex tasks. From the early simple operations of microprocessors like the SAP1 to which is a simple as possible computer, or basically a mini computer, to the now sophisticated 32-bit processors with pipelining and advanced memory management. We've seen how CPUs have evolved to improve performance over time. The rise of GPUs with their ability to perform parallel processing for graphics rendering and AI tasks, highlighting the growth need for specialized processing power. And by understanding all the fundamental operations of microprocessors and how programming interacts with hardware, we are also able to gain insight into how these systems work together to drive technological advancements. And this foundational knowledge prepares us for the future of computing and its ever-expanding possibilities. So that's all from me. And once again, for the last time, my name is Castro from DCPET 31. Thank you all, have a good day, and see you when I see you.